Well, sorry, my video was interrupted, but what I wanted to say is that in the ideal situation, the output voltage swings between VCC on the positive side and VE, which is a negative voltage on the output side, as established in the previous lecture. But in a practical situation, it doesn't really reach VCC. It goes to a maximum of VCC minus VSAT on the positive side and a minimum output voltage of VEE plus VSAT. Of course, VEE is assumed to be a negative voltage. That's why it reduces after adding VSAT to it. So you always have to remove a small voltage of the value of VSAT on the positive side to get the maximum output voltage. And if you know the VSAT, of course, of the amplifier, and if you know the VSAT of the amplifier again, to get the minimum output voltage, you have to add it to the VE, which is a negative value, to get the minimum output voltage of an operational amplifier. Of course, all of that goes with the assumption that the operational amplifier considered here is supplied by VCC, which is normally a positive voltage, and VEE, which is normally a negative voltage, such as minus 15 volt, minus 12 volt, etc. Okay. We carry on with the most common applications of operational amplifier. So after summing, difference, amplifier, with its two application, instrumentation amplifier, noise cancellation, we now jump to the use of operational amplifiers to design what we call active filters. How can we use an operational amplifier to design an active filter? And here we're going to look at a low-pass filter. We're going to look at a low-pass filter. We also will look at, of course, it's an active one, and I'll explain the difference. Because if there's active, that means there exists passive as well. We will also look at the high-pass filter. But before we go there, probably some of you don't know what a filter. What is this thing called a filter? And I'll try to link it to a practical application scenario, which is your project, basically, which is directly related to your project. Remember, so far we've been analyzing different circuits in terms of different circuits and signals we've been analyzing so far have been analyzed in terms of time, their time behavior. For instance, if you say it's a sinusoidal signal, you'll analyze its amplitude, how it changes in time. You'll analyze it phase out, it varies in time, at what frequency and period it is. Everything has been with respect to time. So now, in most electronic applications, we just don't have to analyze the circuit with respect to time. We can also analyze it with respect to frequency. So if we start looking at an amplifier and say, how does it, after amplifying obviously the circuit in terms of time, how does it behave in terms of frequency? We come up with what we call a filter. And as you know, filter says cutting out something, right? When you speak about a filter, what clicks in your mind is that you are cutting out something. Okay, and cutting out something would refer also to passing something. So what do we cut out? What do we pass out in? It's actually frequencies. Because at the end of the day, the signals, the way they appear in nature, they are not just pure as we draw them in time in our analysis. They are not just pure like that. They normally come sometimes superimposed with some other unwanted signals that we can call noise, for instance. Or in another typical scenario, we happen to mix two signals together to get one composite signal. But the difference between the main signal and the unwanted signal that I've drawn here is that they are both at different frequencies. That is it's slower, so it's at a longer period, so it's at a lower frequency compared to the noise. You agree? The noise is normally, the superimposed signal is normally at a faster frequency. If you have to work out its frequency, since its period is very small, its frequency obviously is higher. So sometimes you might, in many applications, including sound applications, you may be in need to remove to clean the signal, meaning remove the noise. How would you then remove the noise? Since the key characteristic that differentiates between the main signal you want and the noise signal you don't want is frequency. Noise is at a high frequency compared to the actual signal, which is at a lower frequency. You just have to design an electronic circuit that we call a filter that will cut out or filter out the noise. So for it to filter out the noise, it only has to pass, therefore, it passes certain frequencies below a certain frequency threshold that we call cutoff frequency, and attenuate. So the circuit will have to have a significant gain, ideally of 1, because you want to pass the signal, ideally, as I said, you want to pass a signal without changing its amplitude, but only the component of that signal that are below a certain frequency. And you're going to attenuate, meaning the gain on the other side will be very small, because we're talking about closed loop gain here with respect to frequency. Above a certain frequency, threshold frequency, you want the gain to be very small, ideally even 0, no gain, so that basically you are cutting out the component of the signal with frequency higher than this cutoff frequency. That type of circuit that will have to have some form of gain, and that way it's normally made up of an operational amplifier and 2 gains, basically, depending on the frequency at which you are, and it's called the filter. But the one that specifically passes lower frequencies and cuts or attenuates, you see the gain is very small there. It attenuates higher frequency than a certain cutoff or reference frequency, is called a low pass filter. Opposite to this, similar to that, sometimes you might be in certain other application, you might want to do the opposite. So attenuate by closed loop gain, AV closed loop gain, AV closed loop. You might want to attenuate lower frequencies than a certain threshold. There's still a cutoff frequency, and pass the higher ones. So you pass the component of the signal, meaning they have a beta gain, while this one have got a very small closed loop gain. Closed loop gain almost equals, ideally equals to 1. You dropping the component of the signal with frequencies lower than a certain cutoff, and you are passing the ones with a frequency higher than the cutoff. And this is a high pass filter. It passes higher frequencies. Both these filters are active because, as you learn in other subjects later on, there's a way to design a filter that will do exactly the same, but with passive component, meaning without any component that needs to be powered to perform its job. In this specific case, it's active high pass and active low pass filter because they both use operational amplifiers that need to be powered. Right. They need to be having an active voltage, 1 or 2 active voltage sources. 1 in the case of single power supply, and split power supply, 2 active voltage sources for them to operate. So that's why we call, since we are designing a filter using an active component, meaning an operational amplifier inside which there are transistors, which are active component, then it's an active filter. You're going to learn in some other subjects how to design a passive filter, meaning a filter without making use of any transistor, just some capacitors, resistors, and inductors. Okay, but in this case, we're talking about active filters. So let's start with the first one, which is the active low pass filter. How would you design an active low pass filter using an operational amplifier? So you can configure an operational amplifier to behave like an active low pass filter as follows. You will have the operational amplifier. The configuration goes as follows: minus plus. You're gonna configure it in a inverting amplifier mode, amplifier circuit, feedback amplifier circuit mode. So RF, R in, and you're gonna apply your input voltage there. Now you can have different values for RF and RI, but sometimes ideally you would prefer to have the same voltage. I mean the gain of 1, which means RF and RI to be the same. But the key difference between a inverting amplifier circuit and an active low pass filter is that in parallel with the feedback resistor, you would normally add an electrolytic capacitor, in this case the negative side being that side because that's the side of virtual ground, low voltage potential, the positive side being on the side of Vout because normally Vout is higher than the voltage that appears there. And by having in parallel a capacitor with RF, connecting here and here, it's the same. So I would have just connected it there as well. It's the same point, basically. Okay. So having a capacitor in parallel with RF results in a active low pass filter. But what is that? How do you then design this low pass filter to have to cut off a certain number of frequencies, and what type of frequencies? Since it's a low pass filter, it's gonna cut off higher frequencies, but higher than what value? So in other terms, how do you design for a cutoff frequency value with your filter? How do you get to choose what will be the cutoff frequency value below which the frequency, the signal component with those frequencies will be passed, and above which they will be cut off? If you look at the gain behavior of this specific low pass filter circuit in terms of the frequency, because we are analyzing in terms of frequency and we are looking at the closed loop gain, we're gonna have the maximum closed loop gain there, and as we go along, we're gonna reach a certain the gain above a certain frequency, the gain will start dropping, and when it drops by what we call minus 3 decibel, we're still going to analyze that just now. The point at minus 3 decibel in terms of the gain here is what we call the cutoff frequency. So now how do we get to choose that cutoff frequency, FC? In terms, how do we get to choose a certain value of C and a certain value of R to design for a certain cutoff frequency? When it comes to the low pass filter configured, the way it is drawn in the circuit is shown here, where we started. The cutoff frequency we obtain, which is the frequency 3 decibel below a maximum gain, will be equal to 1 over 2 pi RF CF. So to design for a certain cutoff frequency of, let's say, 100 Hz, one will choose a specific RF and work out CF, for instance, using this equation, or choose CF and work out RF. Those are the type of problems we normally give you. But what will be the voltage gain of the amplifier? The voltage gain of the amplifier will be minus, remember normally without considering the frequency aspect, meaning without the capacitor, with no capacitor it was minus RF, supposed to be minus RF over RI, because it's an inverting amplifier mode. So that's what it would be without the capacitor. But as you've learned in electrical engineering 1B or electrical engineering 2 for those in the old diploma, you've learned that when you have a resistor together with a capacitor or an inductor, you build what we call an impedance. And this could be in series or it could be in parallel, like it's our case here. You still build up an overall impedance. So what happens here is now the gain with the capacitor connected to the rest of the circuit will be minus ZF over Rin. On the output side, on the feedback side, we now just don't have a resistor. We've got a resistor RF, feedback resistor, with a feedback capacitor CF in parallel, making up what we call ZF, or feedback impedance. But now, how much impedance do we have? How much is ZF? When you've got a capacitor and a resistor in parallel, as you learn in electrical engineering subject, well, that to calculate the overall impedance, we have to first calculate what we call the reactance of that capacitor. So the reactance of CF, which is XCF, as you know, is normally what is the reactance of CF is normally 1 over 2 pi f CF. Right, the same way you recall the reactance of an inductor is 2 pi FL, right? So the one of a capacitor is normally that. But now, so at the end of the day, we've got impedance wise, you've got XCF, right, as an impedance in parallel with another impedance made up of a resistor only, which is RF. So what will be the total impedance? It's going to be 1 over XCF plus 1 over RF, all of it to the power minus 1, and that will give you RF plus XCF over XCF times RF to the power minus 1. So at the end of the day, the total impedance ZF is nothing but XCF, which is the reactance of the capacitor, times RF over RF plus XCF. That will be ZF, and as you know, that will be in electrical engineering, that will be a how do you call it? It's gonna be a complex value. But now, what we will use to calculate the gain is not the complex value. It's gonna be actually the it has to be the magnitude of that complex value over RE. So it's actually, we're referring, when we said ZF earlier on, we refer to its magnitude. And as we know, in terms of magnitude, the magnitude of RF plus XCF, because it's actually RF plus XCFJ, the magnitude of such a complex number is square root of RF squared plus XCF squared. So that will lead to ZF, the magnitude of ZF being XCF as a value, RF as a value multiplied, divided by square root of RF squared plus XCF squared. Okay, all of these are concepts you normally learn in electrical engineering 1. So that will lead to our gain being equal to XCF RF over square root of RF squared plus XCF squared, all of it divided by Ri with a minus there. That will be the gain. Right. So now that is the gain. Of course, here when we say ZF, we're referring to the magnitude. That is the gain as a proportion, meaning in volt per volt, as a proportion. But now comes a new concept of what we call, and this concept is often used when we do any form of frequency analysis, meaning we're looking at a signal with respect to frequency. It's what we call a decibel. The decibel concept was invented by Bell, and it has to do, as you know, because it's voltage ratios. So to calculate the gain voltage in terms of decibel, you would use 20. If it was pi, we were going to use 10. So 20 log of the gain as a proportion. So that will give 20 log of ZF over Ri. Where did the minus go? Where did the minus go to? You recall that if you have to do logarithmic of a negative number does not exist. So we look at the gain. We are actually looking at the magnitude of a gain instead of the actual gain itself with its sign. Okay. That's more or less it. So now, how do we get XCF? XCF is, as I mentioned, is basically the XCF is basically the reactance of the capacitor, and as you could remember, its formula 2 pi over 1 over 2 pi FCF involves some frequency. But what frequency is that? How different is that frequency from the cutoff frequency we are considering here? To answer that question, we will normally be given the operational frequency. That frequency, first of all, is different from cutoff. And this frequency at which we are calculating XCF is the frequency of operation of the operational amplifier. And that will be normally given to you. So for instance, if you look at example 5317, it clearly said that the amplifier is operating at 0 Hertz in one case and at 1 megahertz in the other case. And that frequency is nothing but just the frequency of the input signal. So that's the frequency of F is the frequency of V in, while FC is the cutoff frequency of the amplifier that we calculate. But F being the frequency of the signal, V in, is what we are given. It's the frequency of the signal we're trying to amplify. So when the signal we are trying to amplify is DC, of course, F is equal to 0, right? And in that case, you get ZF, XCF basically to simply be equal to 1 over 0, which is infinite, which makes infinite in parallel with RF. Infinite in parallel with RF. So ZF is just reduced to RF. That's the purely DC case scenario. But when we have V in at a certain frequency, it's not a DC value, but it's rather a signal at a certain frequency F, then there will be XCF that will be existent, and we have to calculate ZF accordingly, according to the formula that I've provided there. So that's it in terms of low pass filter design. When it comes to a high pass filter design, they use active